Los pingüinos me la van a mascar. Kawasaki, Kago, Crico y Stripper.
So we can see that what the code does create a square wave. The goal is to build a square with a signal that switch between two levels using a mathematical method called Fourier series. Using a harmonics to create the square wave, the code adds a multiple size wave which are called harmonic. Only the odd harmonics such as first, third, fifth are used. Tests with the different number of harmonic. The code tries three cases using a 5 harmonic, 10 harmonic, and a 20 harmonic to see how the adding more sine wave make the square wave look more accurate. The result of the codes in the time domain with the 5 harmonic, the square wave looks rough and not very sharp. With the 10 harmonics, it looks better with the sharper edge. With the 20 harmonics, it looks almost like a perfect square wave. In the frequency domains, the graph shows peaks at the odd multiplies of the base frequency, fundamental frequency. These peaks represent the harmonics that contributes to forming the square wave.
Hello everyone, today I'll walk you through this MATLAB for analyzing the frequency response of an RC low-pass filter. First, we define key parameters. Fc is the cutoff frequency at 1130 kHz, and Fs is the sampling frequency set at 10 times Fc. A frequency vector f is generated for analysis. Next, the script calculates the filter's magnitude response using the formula. The gain is then converted to decibels using 20 log 10 HF. Finally, we plot the frequency response. The x-axis represents frequency in kHz and the y-axis shows the gain in dB. The curve demonstrates how the filter attenuates higher frequencies. Initially, at low frequencies, the gain is close to 0 decibels, indicating minimal attenuation. However, as the frequency increases beyond the cutoff point, the gain starts to decrease, exhibiting the filtering effect of the RC low-pass filter. This graph effectively highlights the key characteristic of low-pass filters.
For my video, I will present task 4, which is analyzing the output signal in time domain and frequency domain using MATLAB simulation. So this is the code to plot the signal. The first code is find the filter signal, which is FT, open bracket, FFT, open bracket, XT, which is the signal in time domain, multiply with HF, which is the magnitude frequency. The next code is to plot the signal for both frequency and time domain. And then we hit the run button, and the signal will be displayed, the output. The above is the filter signal for time domain, and the below one is the filter signal for frequency domain. So for time domain, the amplitude reach until for high state is 0.8, for the lower state is negative 0.8, and the sharp transition indicate a rapid change in amplitude, which means that the presence of high frequency component is available in the signal. So the next part is the filter signal for frequency domain. So in this signal, it shows that the amplitude value is reduced as the frequency increase, which means that the filtering operation may have been applied to reduce a certain frequency while maintaining or preserving the other frequency.
Our group got the value of F node is 300 kHz and FC cut frequency is 1130 kHz. After manual calculation on finding the value of resistor and capacitor, the value of 140.85 ohm, and for the value of capacitor 1 nanofarad. Then we need to create the transfer function of RC circuit in MATLAB. As you can see in the coding, transfer function is what the function TF stands for. It is used to generate discrete time and continuous time transfer function, which is characterized the frequency domain connection between the system input and output. In this figure show a dot plot for RC low pass filter. A simple circuit known as RC low pass filter decreases high frequency signal while permitting low frequency information to flow through. A dot plot shows two characters in it. A magnitude plot expresses the decibel, illustrates the frequency dependent change in the output signal magnitude. A phase plot expresses degree, illustrates how the input signal phase varies with the frequency. The RC low pass filter eliminates unwanted signal or high frequency noise. The dot plot is an effective tool for circuit analysis and design since it clearly shows how the filter behaves at the various frequencies.
I'll explain this MATLAB code, which analyzes square waves with different duty cycles and their behavior after low-pass filtering. First, the fundamental parameters are defined, including the period t0, frequency f0, and the time vector t. The cutoff frequency of the filter Fc is also specified. The filter's frequency response is calculated using the formula for an RC low-pass filter. The code analyzes square waves with duty cycles of 10%, 20%, 30%, 70%, and 80%. For each duty cycle, the square wave is generated by setting the pulse width tau, creating an on and off period in the time domain. Next, the Fourier transform of the square wave is computed to observe its frequency spectrum. The low-pass filter is applied in the frequency domain, and the filtered signal is reconstructed back into the time domain using the inverse Fourier transform. The results are plotted in three subplots for each duty cycle. 1. The original square wave in the time domain. See the square waves in the time domain for duty cycles of 10, 20, 30, 70, and 80%. The pulse width increases as the duty cycle rises. 2. Its frequency spectrum. The frequency spectra of these signals reveal their harmonic components. As the duty cycle increases, the strength of the fundamental frequency and its harmonics changes. 3. The filtered signal in the time domain, showing the smoothing effect of the filter. The filtered signals in the time domain demonstrate how the low-pass filter smooths the square waves by attenuating the high-frequency harmonics, leaving a rounded waveform.
That's all for me. Thank you very much.